So last day, we've been looking at horizontal circles. Patrick, you missed some pretty cool applications. We looked at artificial gravity. We said that if you're a space station and you spin it, if you build a circular space station, normal force is what's causing you to move in a circle. And if you know what you want the normal force to be, 80% of mg, 70% of mg, 50% of mg, you can figure out either how fast you need to spin the space station or what the period of the space station needs to be or what the radius needs to be if you know how fast you can spin it. Then we looked at the Gravitron, which was the amusement park ride where you lean against the wall and it starts to spin and then the floor drops away. And we said it's actually the same physics as the space station, except since you're on Earth, gravity is pulling you down. There has to be a force pushing you up. And we thought about it for a while, and we said, oh, friction must be what's pushing us up. This ride would not work if the wall was made out of ice. That would not work. Then we looked at another application where we had a string on the end of a mass, and we were spinning it around, and that was pretty cool, too. And this is where we got to mention error on formula sheet, so I did that. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. Going around a corner, but instead of the corner being flat, it's banked. Gurjot, we have done going around a corner when the ground is flat. That's where I did my very impressive stick figure diagram of the car headlights coming out of the page towards us and all. And that some corners, typically subdivision corners and things, are flat because you're not going very fast. But you may have noticed if you're, for example, coming off the freeway and hitting the off-ramp, that corner is not flat. It's banked. It's curved. This is a really neat application. It says this. Suppose an engineer is designing a curved exit ramp coming off of a new freeway. He or she decides to make the corner a banked corner with an angle theta, as shown in the picture below. He or she wishes to remove friction from the equation. We want this road to be safe even if it's icy. So here's one situation. Suppose the corner has a radius of 55 meters and theta is 23 degrees. What speed limit should we post for drivers approaching this? So first of all, there's a small typo in the diagram. I couldn't get that tire to touch. This tire should be touching because right now it looks like the car is about to fall off. That tire should be touching. Sorry, I couldn't get that to quite work. This car is going to go around in a circle, and I want you to notice, Linnea, the circle is horizontal. It's this circle right here, kind of level with the center of the car. That's the circle that we're going through. So, Sarah, what path is this car tracing out? Where must the winning force be pointing? Toward the... What are they asking me to find? I think I'm going to use the one with the V in it, not the one with the T in it. You know what this is a job for? Free body diagram. Except here, I have to, Sharon, get you to forget a habit that I've drummed into you. We're going to do the free body diagram. Instead of labeling the picture, I'm going to do it over here. I'm going to represent the mass with a dot. And I'm doing it on a separate picture for a reason. Sarah, what are the forces acting on this car? Get the obvious one. Which way? Yeah. That's why it's the obvious one. What else? Does that show up? She said something towards the center. Does that show up on our free? Does FC show up on our free body diagram? Nope. What else? Is this car sinking into the ramp like quicksand? Is it flying into the ramp, off the ramp like Superman? So, and the normal force is going to be up like this at an angle. Let's label that better. The normal force is going to be up like that at an angle perpendicular to the ramp. Did I say angle? This is not a job for components. And this is the habit now I have to drum out of you, Paige. And the reason is we went to components because when we were looking at forces, we wanted everything to be in line with the ramp. But this time, Sarah, the circle is horizontal. It's in line with the ground, not the ramp. So here, components would make it tougher. Those are the only two forces acting on it. Is there friction? We're assuming that we're on ice right now. We want to find out what speed limit doesn't require friction, so no friction. What I want to do instead of components is I want to add these two vectors together to find the net force. How would I add two vectors together? Draw them. So it's going to look like this. Now I have two vectors. One is slanty, one is nice. When I have two vectors, I always draw the nicest one first. Which is the nicest one here? Gravity. So I'm going to draw gravity like that. And then from the tip of gravity, don't write this down just yet, I'm going to go up with a normal force. But here is the beauty. What path is this car tracing out? So where must the net force be pointing? Toward the... In other words, I know that the resultant is going to, don't write that down, is going to look like that. Tell me when to stop drawing the normal force. Let's try that again. Tell me when I have to stop drawing the normal force. This is the beauty. Because I know what the answer has to be, that's what helps me figure out how this triangle is going to fit together. That's the normal force. The resultant is from the tail of the first to the tip of the second, and that is my centripetal force, my circular force. Did it show up on my free body diagram? Does it show up on my vector triangle? Oh yeah. Oh yeah. If you play around with the angles and if you add a bunch of extra vertical and horizontal lines and things, you'll find that this theta here ends up being that theta there. And they look like they're the same two angles because it's the thin pointy one and the thin pointy one. So now that gives us lots of options. First of all, FC, opposite, adjacent, or hypotenuse. What about mg? What about the normal force? I'm going to leave the normal force blank. I'm going to look like it's labeled, but I'm not going to put the H on there. What are we trying to find? Which I think is contained inside there. Yes? Do I know the normal force? Do I know G? Yeah. Do I know the mass? I wonder maybe if it cancels. The fact that I know G, I'm going to start out trying to solve this using those two and not the normal force. Which trig function? Good. So I get this. Tan theta equals FC over mg. What do you think I want to get by itself in this situation? Yeah, how? So I'm going to get mg tan theta equals, and you know what? Instead of writing FC, F equals what? F equals what? MA, and since we're moving in a circle, it's going to be AC. Which one of the ACs am I going to use? More specific? Good. I did two steps in one there, but was that okay? We moved the MG over, and then I said, I know FC is MAC, which A? Okay. Do the M's cancel? So you're saying semi-trucks and motorcycles can both use the same off-ramp? We don't have to have separate exits for bigger vehicles and smaller vehicles? There's why. I like this question. I like this question. I like this question. As far as I'm concerned, I can either give you the radius and say how fast, or I can tell you how fast we want to go around the corner and say, what's the radius need to be? What are we trying to find here? How would I get the V by itself? And do you notice we got our square root of GR with other stuff as well, but we got our fairly familiar, I'm on familiar ground. I get V equals GR, and there's still a tan theta square root. This is the speed limit going around a banked corner. It's going to be 9.8. I've scrolled down. Sarah, what was the radius? 55? What was theta? 23. How fast can we take this corner? Now remember, by the way, while in the horizontal, when the corner was flat, friction had to be there because friction was what was pushing us in a circle. When we did our free body diagram, friction equaled MAC. Here, this works, no friction. This could be made of ice. We're still safe. What do you get? Is it 15.1? Yeah. I didn't do that in my head. I remembered that from this morning. Supposing it was a really, really, really icy day, and suppose the road was covered with ice, what would happen if I hit this too slow? Patrick, what? I would slide this way, inwards. What would happen if I hit this too fast? I'd slide off. And so when you see those bank corner off-ramps, when you see that speed limit, if it's icy, do that speed limit. Don't slow down. Don't speed up. Do that speed limit. Otherwise, you could end up with trouble. And you actually see that sometimes. You'll see people have slid to the inside. Otherwise, why would they have spun out towards the center? They must have done that because I've seen cars in the ditch towards the center of those off-ramps on icy days too. They went too slow. So, too slow, you'll slide inwards. Too fast, you'll slide outwards. Now that's if it's pure ice. If there's friction, which there normally is, you actually have a range of values you can get away with, because if you do go too fast and your car wants to slide up the ramp, friction will push you down the ramp. And as long as your tires are fairly sticky, that gives you a fairly big extra force that can come into play, and it gives you a range of speeds that you can go to. Oh, and if you go too slow and you start to slide down, friction can push you up the ramp. And so instead of 15.1, in real life, on a dry, nice day where the pavement is dry, you've probably got a plus or minus range of several meters per second. Certainly also, this is how you build racetracks. You bank the corners so the cars can go really fast. Example 6. Suppose we are an engineer designing a racetrack, and we have a banked corner that has a radius of 165 meters, and we want the drivers to be able to travel at 45 meters per second. What angle theta do we need to build the track? Cool. Kieran, what path is this car tracing out? A circle. You know what it's a job for? Yeah, in fact, I'm going to dulp first, I think, since they didn't give me a picture. So what I'm imagining is there's the racetrack. Here's the car. I'll have it coming towards us. So the center of the circle is over here. It's a horizontal circle. The ground is angled, but the circle is not. This is a job for a free body diagram. And this time, Kieran, they want me to find angle theta. What are the forces acting on this, Kieran? Get the obvious one. Yep. What else? Is there an angle? Yeah, this time, though, we don't want to do components. And that's really the trickiest part. Kids always want to do components because I've taught you too well. I've drummed it into your brain, Ange. But can you see why here, the circle, it's parallel to the ground. I don't want perpendicular and parallel to the ramp this time. Instead, what am I going to do here, Kieran? I'm going to take those two vectors and add them together. How? It's going to look like this. Gravity. Kieran, tell me when to stop drawing the normal force. How do I know? Because I know the reason we can use this is we know what the answer has to look like. It has to be pointing towards the center of the circle. And since the circle is a horizontal circle, the force must be a horizontal force. Again, Sarah, did FC show up on the free body diagram? Nope, those two red forces are the free body diagram. It shows up in my equation. In this case, instead of going winner minus loser and breaking everything up, I'm adding them together to get the net force using vector math. I'm doing the same thing but with trig. And this is angle theta here. Kieran, FC, opposite adjacent or hypotenuse. Opposite, what about mg? Now, is it always going to be tangent? It will if you're starting with mg. If they gave me the normal force, I could use those, I guess, and that would be sine. So another equation that does show sine is FC over Fn. And there is a cosine equation as well, mg over Fn. But usually we start out with FC and mg because those are the ones we want to find. Okay. Tan theta equals FC over mg. What am I trying to find, Kieran? Oh, you know what? I'm going to leave the right-hand side. I'll get a decimal, and I'll go shift tan. Although, let's do some substitution here. I get tan theta equals MAC over MG. Can semi-trucks and motorcycles both go on this track? Yay. Which version of A am I going to use? Okay, so I get this. Tan theta equals, where most kids struggle is the fact that most of you suck at fractions. So what's A? Can you just say it out loud, nice, loud, and proud? I've already drawn the over the. There was already a G on the bottom there from the previous expression. What's A? Oh, don't do that, Mr. Duick. V squared over R. That's how it all fits together. Okay. I've scrolled down. Can you give me the numbers? What was V? Very fast. That's about 140 kilometers. Yeah, it's a racetrack. 140 or so kilometers per hour. G, 9.8. What did I say R was? What do we need to... oh, sorry, I can't say tan theta equals because it's not tan theta. Theta equals... What do we need to bank this track at? So get that as a decimal and then shift tan. You get, I think you get something in the 50s, if I recall. 51.4. Which is pretty steep, but not crazy steep. How many of you have seen the movie Talladega Nights, the Will Ferrell comedy from years ago? There's the scene where he goes loopy and he's running around in his underwear. He's running on a banked corner. That is the Daytona Speedway corner. I think that's at about 46, 47 degrees. I stuck it in your homework. I looked it up because it's a very famous racetrack corner, and so you'll look at it for homework. But you would have a tough time walking on this. Anything above 30 degrees, we just aren't used to it. It's not that we can't keep our balance, it's that our feet can't bend very well to give us enough friction. It just gets tiring and awkward to walk on. Okay. What's your homework? Every question. So 1, 2, 3. I already assigned 1, 2, 3, 4, 5, but now you can add number 6, number 7, number 8, number 9, number 10. Oh, there's the Daytona Speedway. 31 degrees. Has a radius of 1,000 feet. How fast should you take the corner? And number 12. I got a couple of videos to show you, though, as well, so put your pencil down. I want to continue with one more neat application from Lesson 5. Lesson 5 I called Cool Applications, and I want to look at roller coaster loops in more detail. We're going to do example 1, and then your homework is going to be the homework from Lesson 4, and I'm going to be giving you a take-home quiz. Really, the homework is the take-home quiz. Here's a roller coaster loop. A roller coaster, and can you see, Linnea, I underlined the word barely and bold fonted it, makes it around a vertical loop of radius 4 meters. Jaden, what does part A want me to find?
Height.
minimum height. It wants me to find that. Is there a change in height?
Yes.
Is there a change in speed?
Yes.
Is there a yucky, curvy path?
Yes.
What might I try to solve this one? Not components. Brian, I think I'm going to try conservation of energy. Change in height, change. I want a scalar approach. I'm going to let right here be initial, and I'm going to let the top of the loop be final, because I want to find out barely making it. How high I need to build this to barely make it over the top of the loop. So put a little F by there and a little I by there. This is a job for conservation of energy. It's going to look like this. Kinetic initial and potential initial equals kinetic final plus potential final. Are any of these 0? I think the only thing we'll assume, Jaden, is that we're starting at rest. We can cross out KEI. But we're not starting out on the ground. We're not ending up on the ground, because final is at the top of the loop. And I know I can't be at rest at the top of the loop. If I was stopped there, the coaster would fall off, come crashing down, and people would die. So we don't want to design it that way. What was the equation for potential energy, gravitational potential energy? Do you remember? MGH. So this is going to be MGH initial equals, what was the equation for kinetic energy? So it's going to be half mv final squared and mgh final. What are we trying to find? H initial. Oh, I already noticed something. Jaden, can little kids and grown-ups go on our ride? Yeah. Oh, why? Okay. To get the H initial by itself, I'll end up dividing by G, but let's just hold off for a second. Let's walk through the right-hand side and see if we know everything. Half 0.5. Do I know how fast I'm traveling right there? Right here. Right here. Hey, what path am I tracing out?
Circle.
Where is my winning force going to be pointing? Toward the
center.
And does the circular motion equation have a V in it? Would that help me figure out maybe what this V has to be? Let's do that. You know what this is a job for over there? Free body diagram. What are the forces acting on this roller coaster? Get the obvious one. Yep. What else? Which way? Yeah, it's always in whichever way your head's pointing. So in this case, it's going to be towards the center. I'm going to analyze the circular part up and to the right here in this white space. Who's winning? It's a trick question. They both are. I get this. Normal force plus mg equals m, and I'm pretty sure I'm going to use the v squared over r because I want a v. Do I know g? Do I know the normal force? What word did I underline in the original instructions? So if we barely make it, what we're really saying is this. You feel like you're about to fall out. If you feel like you're about to fall out, if we barely make it, how big is the normal force? 0. We can assume that this is 0. Why? Because of the word barely. So I actually get this. mg equals mv squared over r. Hey, Jaden, can little kids and grown-ups still go on this ride? Yes. Oh, that's convenient. And I'm going to get the v... Wait. I'm not going to get the v by itself. If I'm really clever, Jaden, instead of getting the v by itself, what will I get by itself? You get the v squared by itself, because that's really what I... Otherwise, I'll end up square rooting and then squaring on the next line. I really want a v squared. How would I get the v squared by itself? At the top of the loop, if we barely make it, what does v squared equal? And I smile because that's familiar too. So I'm going to plug this in down here. I'm going to get GH initial equals, I'll replace the 1/2 with a 0.5. Grr. Plus G, I'm going to pause here. Now the final height, what would a clever way be to write that height? What would a clever way to write that height be? Better than a diameter, because I don't have a diameter anywhere as a variable. Zach, what?
2R.
Loud and proud, what?
2R.
Why don't I call this twice the radius, and so here, instead of an H, I'll put a 2R, which is the height of the roller coaster final. Oh! Ha! Would this roller coaster also work on the moon? Why? Look carefully. Chang, what? So if the G's cancel, that means this would work on the moon, or on Mars, or on any planet in the universe that we could put this roller coaster on. We wouldn't have to change the height or anything. It would work. You see the G's cancel? We've had this happen a couple of times this year, and we always get a little nerdy smile. But not only that, now, look at how ugly we've started out with, how much work we've done. We get a clean answer. You know what your initial height has to be? 0.5R plus 2R. In your head, simplify. What is 0.5R plus 2R? Don't overcomplicate it. Chang. No, don't overcomplicate it. Yeah. Huh? No. How about 2.5R? I'm willing to bet that every single ride designer, the same way all of you have memorized when I say, get the obvious one, MG pops into your head, I'm willing to bet that that's something that ride designers have at the tip of their fingertips. Now we can plug in numbers. But again, I love the fact, look at all this work that we've done, and you get such a clean expression. You want to build a roller coaster that's safe, your height, your initial height, your first hill has to be at least 2.5 times the radius of your loop. Otherwise, they can't make it through. And now we can actually do this in our heads. And Jaden, you're going to do this in your head because R was 4, so you're going to go 2.5 times 4. What's 2 times 4?
8.
What's 0.5 times 4?
10.
It's going to be 10. Now, that's minimum. You'd probably build it higher, and that would give you a safety margin. No, you wouldn't. I've completely lied. Nobody would build this. I'm going to show you why. What's B want me to find, Chang? Where? Okay, so now we're talking about right here. What path is the roller coaster tracing out? You know what there's a job for? What are the forces acting on the coaster at the bottom? Get the obvious one. What else? Which way? What's my equation going to be here at the bottom for circular motion? Who's winning? Has to be, because winning is always pointing towards the... So with authority and without confusion or questioning in your voice, who's winning? Who's losing? And I'm pretty sure we're going to go with the V squared over R one again, because I'm pretty sure we're going to find V. So if I want to find the normal force ends up being mg plus mv squared over R. You okay with that? Do I know M? I think I said 50 or so. Do I know G? Yep. Do I know V at the bottom? No. No. I know that I would have sped up, going back down. You know what? We can find V at the bottom because V at the bottom has to be the same V right here before we hit the loop because energy's got to be conserved. So we can find V, since it's a change in height and a change in speed and a yucky curvy path, by using conservation of energy. G. What I'm going to do, and you can all do this as well, scribble out the F right there. That's going to be my final now. But right before I hit the loop, because that'll be the same speed as right when I come back to the bottom of the loop, because whatever energy I lost going through the loop, I would have gained coming back down the loop. With me? So draw a little line like this. It's going to be kinetic initial, potential initial equals kinetic final, potential final. We're still assuming we start at rest. Oh, but this time we're back on the ground. Yes? So this time I can do that and cross out potential energy final. Yay! Potential energy initial, that was mgh initial, and that equals a half mv final squared. Chang, can little kids and grown-ups still go on the same ride? Oh, that's convenient. And I'm going to get the... Actually, you know what? I'm not going to get the V by itself. If I'm really clever, what should I get by itself? Okay, so I get this. VF squared equals 2GH initial. How else can I be clever? Can anybody see it? How else can I be clever? Can anybody see it? How else can I be clever? Can anybody see it, Chang? What's H initial algebraically the same as? Loud and proud. So you're telling me another way to write this is 2G times 2.5R. That I can replace that V squared with that. Watch what happens. We're going to get mg plus, there's an m, and there's an r on the bottom. But what am I going to write instead of v squared? 2g 2.5r. Oh! In that second fraction, what happens to the r's? Because there's an r on the top and there r on the bottom and everything's being multiplied. So that was convenient. I do have a 2 times 2.5. Jaden, in your head, 2 times 2.5. So we get this. mg plus 5mg. What is that? Algebraically, simplify that, Jaden, by gathering like terms. What is mg plus 5 mg's? No. Chang. Math 9. You know what the normal force is at the bottom? You're pulling 6 G's. Is 6 G's comfy for people? No. No. Oh, by the way, that's minimum. That's if you barely make it. If you add a safety margin, now you're pulling 8 G's or 9 G's or 10 G's. 10 G's is right around when bones can start to break. So we do not design circular loops. Nobody does. That's a lie. As I understand the history, the very first circular looped roller coaster was in the 1930s at Coney Island in New York. And the way it worked, it was a stair that you climbed up, a big stair, and then they just had a ramp that went down. You sat in like a little mining car, but instead of having the ramp go straight down, they added a circular loop near the bottom. And it was so bad, they had to have permanent ambulances and nurses stationed at the bottom. People would regularly get off with nosebleeds and whiplash, but they lined up for hours. This is just the coolest thing! Because in the 1930s, they didn't know any better. Now we know better. So what we do instead of using a circular loop, we use what's called a clothoid loop. And a clothoid loop is teardrop shaped. If you want the official mathematical definition, it's a loop of constantly decreasing radius. The radius is always getting smaller. There, you'll pull far fewer G's at the bottom, but we cannot analyze that with our Physics 12 math. Calculus would be helpful here. If you have a radius that's constantly changing, that's what calculus was designed for. So the next time you're doing a roller coaster that has a circular loop, look at it from the side. You'll see it's not quite a circle. Or, the closer it is to a circle, the more G's you're going to pull. How many of you have been on California Screaming at Disneyland? So that loop, I've looked at it from the side all the time. To me, it looks like a circle. It's not. It can't be. But it's close enough that you're pulling some pretty good G's there. Whenever I go on it, because I'm a physics nerd, I always, when I'm about to hit the loop, either lean forward, and then at the bottom of the loop, I'll try and straighten up, and I usually can't. Or, when I'm in the loop, I'll stick my arms forward, and I'll pump them up and down, trying to do this, because it's really tough when you're inside the loop. You're pulling some good G's, because it's still a clothoid loop, but that one, they clearly pushed how far they can make it circular. Is that okay? We will assume, if I give you a roller coaster loop, that it is circular, because that's the physics and the math that we can handle. But I do need to point out, no one would ever design a ride where you're pulling 6 or 7 G's. Not a chance. The max they'll push off is about 4.5. There is one ride at Playland where you pull about 4.5 G's. When you go on your physics field trip, I'll let you figure out which ride that is, which one that is. Your homework is the homework from lesson 4. Actually, your homework is the take-home quiz I'm about to give you. But first, I also have a cool video to show you.